Hello to everyone. My name is Florin, and I will speak today about my experience and avenue on breast cancer detection and what we achieved in a couple of experiments. So I hope that this will work. Yeah. All right, so we start with a problem statement. If you look a little bit on the breast cancer diagnostic stages, there are 3 of them, starting from stage 1 to stage 3. In diagnostic, we spend a lot of time in stage 2, which is clinical evaluation, diagnostic, and staging. Typically, this stage, the stage 2, is taking something like 4 weeks, could be taking some cases as well 6 weeks or more. And this is very important because we have to actually go to the stage 3 of giving the treatment very fast, especially if the cancer is actually prolonging and is moving fast. So a little bit on the background on those stages. First, when you have an issue, first of all, you have to do a clinical evaluation, right? So we have to go to your doctor and just have something like early evaluation. And after that, if something goes wrong there, you have to go and do a mammography, which typically some women after 44 is just doing regular at 1 year interval. But you have to do this. And if then they find something, then say, okay, you have to go to the next step, which is ultrasound. In some countries, they skip the ultrasound step and they go to the next one, which is MRI. That will give you a 3D perspective, what's going on there, more accurate. And if that confirms that, okay, there is a tumor there, the question is what kind of tumor is, right? Is malignant, is benign, and what type? That's very important. And then you go to the next one, which is, you have a surgery, a small surgery, which is a biopsy to take a small piece of the tissue from there, which is typically is guided by the doctors. And then they analyze that into a lab for 3 weeks, in lucky cases for 2 weeks, but in general it takes 3 weeks, in some other cases 4 weeks, where you have to wait for an answer. And in the lab test, you get the type of the tumor, you get the grade, the receptors, and based on these, you actually get the treatment. This is very, very important. It's a crucial step in detection of the type of the cancer that is there, especially, for example, if it's HER2 positive, that's something that the lab test will actually give. Now, a little bit on the breast cancer diagnostic, we see here, this is coming from the National Cancer Institute in UK, 5-year survival rate. So early detection, you have 90% by statistics, according to them, to be cured. And then advanced stages, which is stage 3 or even 4, very, very few chances as a survival rate. And this is very crucial to have a detection earlier, right? So that if you look at it a little bit in the detection part, the lab is taking the most of the time and where you spend a lot of time assuming that all these, let's say, appointments with the doctors are well done. Now, a little bit here on the stage of the breast cancer, if you are having in early detection, you have 98% survival rate. But as the cancer is progressing and you go earlier, or you are getting, let's say, a chemo or radiotherapy after a while, then if the cancer is progressing so fast, it can be spread into the lungs, into the brain. Those are typically for the breast cancer, the next organs where they spread. So it's very crucial, to cut let's say, the tumor, the type of the tumor, and to give the right treatment as fast as we can do. So one of the questions was, can we accelerate this process with deep learning? Can we accelerate part of it at least? And the one that we are spending in the biopsy, in the histopathology, where you have the tissue, you actually look on the microscope to see what kind of cancer is and so on, and to detect then the type. So to have let's say, a better look on that, we have to a little bit step aside to say, okay, I have this great technology, these convolutional neural networks, can I apply them? what is the legislation around that? And this is a code from FDA in the United States defining software as a medical device, because ultimately we want to have an algorithm to train to recognize, let's say, in an image, a type of a cancer. So that falls into the software as a medical device, where you can see here the definition. The International Medical Device Regulation Forum, IMDRF, defines software as a medical device as a software intended to be used for one or more medical purpose that performs those purposes without being part of the hardware medical device, right? So if you take this a little bit, say, okay, I want to apply this, then the question is, what is the general context? And again, you can go ahead and say, okay, I want to look again to FDA, say what, how they are seeing the applying of those algorithms. And here is the product lifecycle regulation approach for AI and ML based on the software-defined medical devices. So not only that, you have to create a device, but you have to maintain that algorithm. You have to monitor that algorithm continuously to get all these kind of metrics. You have to actually track and log anything that then the algorithm will produce. So it's not that easy that I'm building an algorithm and then I'm putting in that in the production. So we need to have the whole pipeline in place, the whole implementation of the AI ops to have this. All right, so a little bit on the AI infrastructure stack. Obviously, we started with the healthcare regulations, and from there we have to understand, the data that we have to handle, the governance around the data, people involved, policies, all these kind of things. And then we have to understand from where those data are coming. So we need the data lake to have those images stored, and we can take them from there for training and so on. We have to distribute the computing. We need those machine learning algorithms, and at the end, we need all this fairness, explainable AI. We have to understand if we have biases in the data sets and how we can remove them. So all those aspects in general are very complicated for the doctors, for the researchers which are on the medical field to deal with them, right? And one of the things was, okay, can we simplify here something? So in order to answer to this, we had to take a look a bit on the breast cancer diagnostic pipeline. In a simplistic view, from the image perspective, we have, first of all, like I mentioned, the mammography part, MRI, and then we have the biopsy where we have the histopathology. In those cases, we produce images and metadata. The metadata is actually when you have an image from, let's say, MRI, you have a DCOM file format, and inside of the header of the file, you have a couple of things like the age, the sex of the person, the unique MRI ID, and so on and so forth. So those are metadata which are very important as well to preserve. So ultimately, we want to capture those images in various stages and then have a deep neural network to train this network to recognize, let's say, a type of a cancer. Either we do segmentation, object detection, or we do classification. As well, we need to have information, the age of the person, because that's very important and typically is inside of those specific file formats. And at the end, we want to give a prediction to the doctor, say, well, the network can predict that with so much accuracy that this is cancer, this type, and probably this size, and so on. So we are concentrating a little bit on the most time-consuming part, which is the histopathology part. Now, another thing is those file formats are coming in specific things, especially if you have more complicated, more complex things, then again, you have to deal with, let's say, other kind of formats. For example, for brain, you have the nifty formats. So you have to pre-process those images and then extract from those images the metadata and the PNG files or the JPEG files that we need to train those neural networks. And then we actually go further to this stage where we have to do the labeling, right? So we have to do the labeling process. We have to, this is typically done by doctors and specialists. And this is we'll create specialized, let's say, data sets for mammo, for MRI, histopathology, and so on. And then we want to actually detect the bias and to remove them from there if there are. And we use AI 360 toolkit, for example, within IBM. And we have a lot of iterations until we get those neural networks on those things trained. At the end, we want to actually have an image. We want to classify that image being a tumor A, B, or being a normal case. And then we want to do more things like localizing that, having the size of the tumor if possible, especially the evolution. And then we want to extract the context, the age of the person and so on from the existing metadata that we acquired. And then we want to have some APIs where we want to say, oh, okay, we want to have tumor prediction, and this is the type of the tumor we predict, and this is the accuracy, this is the intersection of union, and all those kind of terms. And obviously, at the end is the tumor description. And this is provided to the doctor, and we can apply this to mammography, MRI, histopathology. That will be the goal. Now, from the perspective of inference, so putting this in the production, we would like to put those inference scenarios either running on a server in the data center or either put it in a medical device, in a small device and embedded devices on the scenarios 3 and 4. Those are the big two things, one which can run on data center and one could run in the hospitals. All right, so from the hardware, we use AC922 system. It's an IBM deep learning system. The reason we use that is because for complicated things where you have to investigate, for example, the cancer which has been spread on the tumor has been spread on the brain, we use better accuracy and more images using this kind of technology. You see here an example, 250 images per second compared with 65 images. Now, from the software perspective, we used PowerAI Vision, and you see left for training and inference and right only for inference. And this is a software that is simplifying the whole landscape. This is focusing on providing the best experience to the doctors for labeling, training, without taking care of all the aspects of deep learning and of the infrastructure beneath. So I'm going to speak about how we use these things, right? So the goal is to actually automate the whole pipeline as much as we can with the technology that is available, it's generally available on-prem, because we see, hospitals that they don't want to send the data due to regulations into the cloud. Right, so the product itself is actually providing a web interface and a lot of APIs where doctors, they can go there and find the images, label those images, do some training by just a couple of clicks for classification, object detection, and in the future semantic segmentation. And in addition, we provide as well informations for if you do inference, if you want to test then those models and see how they perform, how good they are. So we provide as well some parts of those models are pre-trained, but we can allow as well things to be added additional on top of the product as custom neural network models. All right, so the experiment we did, it was by using the VRI lab Department of Informatics in Brazil, that they were quite kind to give us their data set for BRAC-HIST called, for histopathology. This was having more than 10,000 images, microscopy images. And the goal was to create a neural network model that will identify those classes, you can see it here, of the breast cancer from the tissues. So benign and malign, but as well, adenosis, adenoma, exactly were interesting to train a network for mostly for atypical cases where the doctors in the lab, they spend a lot of time. So we use for neural network model classification, GoogleNet class activation mapping, where especially on the high resolution, on a 40x magnification of those images, we can actually identify the part in a specific class. And this tends to be very, very good in terms of accuracy. So a couple of screens here about the experience. So you connect as a doctor to the system. You start loading your data sets, creating the categories that you have. You see those are the images that we have. Given on the left side, you will see the classes for each image. And if you want to view the image and have more deep knowledge and check those images in addition to what has been given and labeled by some others, you can go there. And then you can, which is just a button, you can start a training. and the network will start training, and then you do this a lot of iterations until you get to the right accuracy. In the initial run, we got 87% accuracy. Obviously, this was not enough, so we said, OK, can we do something else, right? Can you change something? And there is a technique called augmentation that has to be used very carefully in those cases. So we used to flip the images to horizontal or rotate them with a specific angle to generate more images from what we had to actually train the network. So when actually you do this, automatically the system will augment the images, and you see them here with A from augment. So again, we trained that, and we achieved 93% in accuracy in detecting those classes. And that is the experiment that we have done. And we believe that the inference in under 1 second to give you 90% accuracy is close to the human error, which is 5%. So we still have 2% that I think can be solved in the field there. So in the inference, when you test this with the validation images, you are getting not only the prediction, you can actually establish the threshold, and you have as well a hit activation mapping. So we can give you this map so you can understand what were the most important features in the class that have been contributing to the image to be classified the way it was. So moving further, what's next? Right? So one of the problems that we see there, because this is a continuous process, is how we can be involved a little bit into the mammography part. Right? Mammography is a little bit different because of you don't have color images, majority of them, so they are just grayscale, and that's a challenge for those neural networks to pick them. So until now, my experience was up to 91% accuracy. Still not enough, but we see promising results. So one of the things is to take as well into consideration this part of the mammographies, MRIs as well. We are looking as well to do post-inference and orchestration. So when you have something like a patient that you have the image from the mammogram, from MRIs, and from the histopathology, you can run them as 3 separate inference processes, and then you can do the scoring, including the aging, the age of the person, the sex, and all these kind of things. So you can have, let's say, a better prediction, taking into consideration the other part, especially if you try to consider the cases where we have, unfortunately, patients that they have, let's say, lung cancer, which is a metastasis. And then that is treated by a doctor which is specialized in lungs. And then we have the doctor which is specialized in the breast cancer. And typically they have to find the time to speak each other and say, OK, what we do with this patient. So for those kind of cases, we can actually have a platform where you can use it to do this kind of scoring among multiple disciplines by using deep learning. In addition, we are interested in actually detect as well lesions, so that we believe that can be done, and moving these things to smaller devices, to embedded GPUs, embedded FPGAs, where it can be run somewhere on a desktop. Up to the moment that you have to understand, I need to put this in the production, what that means, how I'm monitoring what those algorithms will do and will predict to advise the doctors in a way or another one. And this goes into the AI operations, how you actually deal with those kind of things, not only on building that model that will actually predict something. And that model has to be put into the context, into the age of the person, into the type of the image that has been used, where it has been used, and what kind of position, and so on and so forth. So we're actually trying to give a platform that can be used for those kind of cases on-prem by the doctors, by the clinicians, so they can train their own networks to advise them, right? To find those cases. We don't try to give them a model and say, use this model, will be the best for you, right? You build your model based on your experience, based on your labels. And the labels, they have to be verified as well by other entities to be sure that those are correctly labeled the way they are. Because those networks, I would say, are very dummy. If you don't give them the right data, they will learn not to predict things that will be accurate or will not generalize well in the production. Questions so far? Yeah.
You're going to get your microphone. Hi, nice talk. I'm Pooja from Nature Research. I'm just curious to know if you're extending your application to any metabolic diseases like liver fibrosis, NAFLD, cardiovascular diseases.
No, the answer is no. That's why we are trying to include as well the context, other kind of things into those neural networks models as a let's say, different pipeline, right? So one of the things is we're taking the images, we are trying to teach those networks for those kind of, let's say, typical cases. But for atypical cases, you have to understand as well the context of the person. So we didn't go that far. We are trying to validate this PowerAI Vision software and how it can be used in such cases. Okay.
Are there more questions? No? Oh, there's one more.
Thanks for the talk. I'm just curious about what is the need of real-time feedback, or why do you need real-time analysis for such a critical cancer detection or something similar to that?
Right. So the way I perceive this is that, for example, when you have an electronic microscope, right, and you actually look for the cells on different magnification, right? As human, at a certain point, you have doubts, right? And in typical, you speak with one of your colleagues. But in general, the algorithms that are displaying you the image are just algorithms. So the need of having a solution like this for the people on the field, if they give them real-time insights, so they can, okay, so the algorithm is telling me that at 40x magnification, I have, let's say, fibroadenoma. The question is, okay, I should go and look a little bit more on a higher resolution, 400x, for more insights, rather than just say, okay, no, it's okay, right? And especially for cases where there are countries where they don't have labs across the country. So there is a long queue, for those kind of cases. How you deal with them? Okay.
Okay, we would have time for one more question, if there is one. Okay, here. Teresa is coming to you with a microphone so everybody can hear you.
Thank you for the nice talk. Can you give a little bit more explanation how doctor will use this? For example, if a doctor has one or two pictures with him or her, so they upload to your system and use your data set, train data set, and then later on check their cases to assist them to make a decision?
So there are two ways. So assuming that the system is in the hospital, because we believe that this system should run in the hospital, trained by the hospital based on their experience and their labeled data. The doctor has two possibilities, either to integrate, let's say, the MRI system via API with the system. So it will get integrated via, let's say, if they use GE or they use other company, via the PACS. Or because we have an API, you just send an image and you get the prediction. Or the second, we'll export the image from DCOM or from NIF, and then we'll actually upload the image via web interface to the system. Then we'll give them a prediction. So there are two ways. Depends of the situation in the hospital.